Physics of vision. If you remember, one of the things we spent a lot of time discussing was the physics of the auditory stimulus, right? And I said it's really important for you to understand the stimulus so you can understand the sensory apparatus that's going to be collecting that stimulus and turning that into neural signals, right? It makes some sense. So that's what we're going to do today. We are going to cover the physics of vision. So for those of you that thought I'm never going to take a physics class, well, you're not. But you're going to get just a little bit of physics in this class. It's going to be exciting because I will make it fun. There's even a guessing game later. Okay, so light, you guys are all familiar with light. Anybody not familiar with light? Monica, you've seen light before, right? If not, just, there it is. All right, anybody heard of Christian Huygens? I'm not surprised. Dutch guy back in the 1600s. He said, light is a wave, and I said so. Okay? And he did some experiments in the 1600s that sort of demonstrated light was a wave. So that's pretty cool, right? So we're like, light's a wave, we can measure light waves, we talk about wavelength of light. Has anybody ever heard that? You know, what about blocking those harmful wavelengths of light by using sunscreen? Right? Okay, so that's a thing. So we think of light as a wave. That's perfectly fine, right? So it's a wave, light's a wave, that's awesome. This guy, Thomas Young, back around 1801, he did this set of experiments, which are super cool, where he looked at diffraction and these interference patterns. So he would take light, a source of light, and he would shine this light through some sort of apparatus, a screen, a filter, variety of things, and he would have, he would draw out the results. And so here, this is a page actually from Thomas Young's notebook. These are results of a variety of the experiments that he performed, where he would take a light source. In 1801, the best light source they had back then was LEDs. No, Regan, they didn't have LEDs. They had things like candles, right? Or sunlight. These are the things that they were using. He would shine this light, direct this light through different substances, and then kind of measure what happened. One of his more famous experiments is called the two-slit experiment. And what he did for this is, and you could recreate this for yourself if you have like a copper wire, electrical tape, and a laser pointer. So we're not going to do that. It's a little difficult to perform in this room with the ambient light being what it is. He had a light source. So this is actually a drawing from that. He had a light source, and he had sort of a screen, or you can think of a piece of paper. He cut two very narrow slits in that paper, and the light would come through those two slits. Okay, and when light comes through, it's going to hit the edges and then it's going to spread, right? Okay, so this is how this works. So the light hits and it's going to spread. What was really interesting is when the light would spread, and the light from one slit would overlap the light from the other slit, right? And so these two patterns of light, these two sources of light would overlap. He found that, not surprisingly, there were areas that were bright, you know, like light overlapping light, so that's pretty cool, right? But he also found areas that were dark. And that's sort of weird, right? If you were taking two light sources and adding two light sources together, how am I getting less light? How am I getting that to be dark? And the reason you're getting that to be dark is because light's a wave. And if you line up the trough of two waves, right? If they're coming from two different sources, you can line up those troughs, and then you have lower light, and if you line up peaks, then you have a higher light, right? So you can have sort of two out-of-phase sources. Let's see. Oh, that's not what I meant to do. And then you have this second, and if they overlap like this, then what you actually have is these two negative regions will add two positive regions will add, right? And so you can have this sort of bigger up and down, and you're actually going to end up with dark spots. So that's pretty cool. And so 1801, we're thinking light is a wave. No problem, right? There's this real problem, though, and his name was Isaac Newton. I don't know, has anyone ever been in a scientific argument with Isaac Newton? Anybody? You lose. That's the rule, right? Anyone versus Newton, Newton wins. Always take Newton over whoever, right? You don't believe me? Ask about that other guy who invented calculus. No one knows his name, right? Because Newton, okay? And Christian Huygens, his ideas didn't really get off the ground very well, okay? I mean, they just didn't make it because Newton said, waves, whatever. Light is a particle. And I'm going to prove to you it's a particle by doing all kinds of light's a particle experiments, right? And so we can measure light as a particle. Now, that's pretty exciting. By the way, this is a portrait of Isaac Newton. No apple, for instance. You know that's a fake story, right? The apple fell on his head, and he's like, whoa, gravity. That's not exactly how that happened. In fact, he was allergic to apples. That's not true either. Hey, look at this brilliant guy. Caleb, I think you should take this picture to your barber and say you want that haircut. Because this is a brilliant haircut, by the way. This is known as the, I think I just made an explosion, but I'm not quite sure because I still can't hear from it. This guy's Max Planck. This is a name you should know. How many of you have heard of the Max Planck Institute? It's a fairly well-known international research university, right? It's mostly based in Germany, but there's actually a Max Planck Institute in Florida. It's kind of weird. They mostly study brain science down there, which is kind of interesting. Max Planck, he really sort of started the quantum mechanics, right? I'm not expecting you to know quantum mechanics, so just relax. He sort of had this idea of quanta, right? And what Max Planck said was that radiation is sort of in the form of these discrete packets of energy, right? And you can measure this. You can measure these discrete packets of energy, these quanta. And if you're doing this with light, then you're thinking, well, that's got to be a particle, right? You can't measure the discrete packet of energy of a wave. That doesn't make any sense, right? But maybe if I'm shooting like particles at you, you can measure how many particles are hitting you, right? And so you can measure that sort of quanta of energy, right? And how many you have. Okay. So he did some great work. What's really interesting, and this is just like a little side story here, because I always like to throw in these side stories, right? Oliver, his son Erwin Planck, actually tried to assassinate Adolf Hitler. It was not successful, and they actually ended up killing Erwin. So you got that going for you. So there's like, I don't know if anybody thought that was an interesting historical footnote. So you've got Max Planck. I mention this because I'm sort of semi-forced to talk about another guy here in a moment, and it's this idiot. This guy is Philipp Lenard. He did come up with this idea called the photoelectric effect. Basically, you can shine light on a metal, and that metal will then eject electrodes. Okay? Some big problems with this guy. One, he was like an advisor to Adolf Hitler. I feel like that's pretty well a disqualifier for about anything else you want to do with your life, right? And there aren't like too many more jobs that are worse than that. The second thing he did is he sort of picked a scientific fight with Albert Einstein, which was even worse than fighting with Isaac Newton because Einstein was like alive at the time, right? And he actually called quantum mechanics that crazy Jew science, which sort of makes some sense if you're an advisor to Adolf Hitler, right? I mean, that's maybe a statement you would make. So we've got the photoelectric effect. Now then this guy came along, Einstein, and being the brilliant person he was, he said, what are you idiots fighting over? Light is both a particle and a wave. And he said, I could explain it to you, but you're not going to understand it, so just assume I'm right, and we'll move on. And that's what the world did. Not really. Justin, there have been a series of other experiments. Light is both a particle and a wave, right? And we're going to think about it as a particle or as a wave as we need to make sense, right? So it can sort of be both. Bonus points if anybody, not real bonus points, if anybody can tell me who this person is. I know there's always these like classic shots of Albert Einstein, right? And I was like, okay, so there's Albert Einstein. But this one I thought was really cool because it had this other guy as well. Anybody want to take a stab at who that is? Not a scientist, by the way. Nobody knows? What if I start drawing things on this guy?
Charlie Chaplin?
Yeah, it's Charlie Chaplin. That's pretty crazy, right?
I've seen him when he's like younger. I've seen him when he's older.
Yeah, no, this is Charlie Chaplin, long before he was played by Robert Downey Jr. Did anybody see that movie? You guys are missing out. So there you go. There's Albert Einstein and Charlie Chaplin. So Einstein sort of solved the problem for us. He said it's just both, right? Who says light has to be one or the other? And there you go. And he's right, as Albert Einstein has often been, right? Even though it took us like 100 years to find those gravitational waves, almost exactly 100 years from the time that he published a paper that said, gravitational waves, guy, it's coming. Watch out for it. Then some physicists got together and they were like, wow, that guy was actually right. It took us 100 years to catch up to him, but whatever. All right, so I like this. This is fun, right, Monic? I mean, it's light is a, and then depending on sort of how you look at this, particle or a wave. I don't know, I thought this was a brilliant sort of, this is what physicists do for fun, right? They make these sort of puzzles. I don't know. So hopefully you can see that this is like a P-A-R-T-I-C-L-E, or it's W-A-V-E, right? And then what I think is like really super cool is the exclamation point, because down here is a particle and there's a wave, right? So they even carried it to the punctuation. Like it's not good enough to just leave it with the letters. Punctuation is going to be part of the joke as well. All right, so that's light. We need to know some more about light. Light is part of what we call the electromagnetic spectrum. The electromagnetic spectrum is huge. Okay. It starts off with these sort of long wavelength waves that carry low energy. Okay. For example, radio waves. How many of you are familiar with radio waves? You guys know what a radio is, right? Okay. So like radio waves, they're very long, right? The size of a building or a human, right? Which is kind of big. These huge waves, low energy, right? Radio waves probably aren't going to cause you any problems. You keep moving to smaller wavelengths, but higher energy. So how many of you have heard of infrared wavelengths? Infrared. Anybody have like an infrared camera? Nobody has an infrared camera. Anybody ever seen an infrared camera, right? So it's sort of a heat signature, right? And they can measure these sort of heat signatures. Who wants a pit viper story? Well, you're going to get one, Madison. So, anybody know why they call them pit vipers? They're really great to put in a pit, and then you can put someone down in there, so with the snakes, and they're all just in this pit together. That's not exactly why they're called pit vipers. They actually have pits kind of on their faces that are sensitive to infrared wavelengths. Okay, and so they can detect heat signatures, which is like pretty cool. They can see like the heat patterns, right? There's this guy in Germany who's really interested in studying like weird sensory capabilities in animals. And here's what he does, and this seems like a really fun job. He grabs snakes by the neck, which in case you want to know where that is, that's anywhere that's not the head. And if you're gonna grab a snake by the neck, it's always better to grab it closer to the head. If you grab it like way down the neck, it can still get around. So he takes these pit vipers, and then So you got to get a hold of the pit viper. He takes electrical tape and wraps the electrical tape around their eyes so they can't see, right? Anybody ever wrapped their eyes with electrical tape? Listen, I know what's happened to people, right? It's Huntington. I know what happens on the streets. Someone, Caleb, has had electrical tape wrapped around their face. It's just going to happen. So if you haven't had that experience, give it a try when you get home. You're not going to be able to see through the electrical tape, right, if you do that properly. And these snakes can't see through. Then what he does is carefully puts the snake back in its cage, right? Got to do that fast. And then what he'll do is he'll put a rat loose. So in case you don't know, snakes eat rats. So that's where this is going. He'll put the rat into the cage, and the snake will still very accurately be able to eat the rat and kind of attack and bite the rat. And that's like pretty cool, right? So you're thinking, well, this snake can't see because I got the electrical tape on its face. But in fact, it's still using that infrared detector system, right, to determine where that, sort of rat-shaped ball of heat is going, and then it can just like snap on there and eat it. That's pretty cool, right? It's kind of exciting. All right, so once you move up from infrared, you get into the visible. We call that visible for one reason and one reason only. We can see it. Obviously, pit vipers can see infrared, right? But we can see what's in the visible wavelength. That's somewhere, let's say, 400 or 500 nanometers up to 700 or 800 nanometers somewhere. And that sort of range is what we're thinking, right? Probably like 400 to 700 nanometers. You move above the visible light, you get into ultraviolet. Okay, who remembers that sunscreen we talked about? Right? So that's the UV light you got to worry about. There are actually some birds and insects that can see UV light, which is kind of cool, right? Okay, it's not terribly helpful to us. But Abigail, what they'll do is you'll have scientists who take pictures of flowers using ultraviolet light, and what they notice is when you do this, there are patterns that appear that you don't see using normal, or what we call visible light, only under ultraviolet light. So if you as a bird or an insect were sensitive to that ultraviolet light, what appeared to be a bland, solid color flower may in fact have patterns, and that would attract you over to like pick up pollen and swap pollen and be this sort of partner in plant sex, right? So that's kind of interesting. I see some like faces like this, like how do plants have sex? They usually use bees. That's why they call it all about the birds and the bees, because birds and bees are required for plants to have sex. So, I have no idea why they say it's about the birds and the bees, right? Have you ever tried to figure that out? Like really thought about that a moment? Like who's getting a bird and a bee involved? I don't know. It never made any sense to me. Nobody's going to comment on that, are they? That's what I thought. Ultraviolet light. Then you move on up to X-ray. I don't know if anybody's been into X-ray. Had an X-ray before, and then you get gamma rays, which I always like to tell people will turn you into Mark Ruffalo.
I understand.
Thank you. I appreciate that. I could say things like Edward Norton or Lou Ferrigno, but I thought Mark Ruffalo would have more cultural relevance to individuals your age, right? Is that true? That's what I thought. So there you go. We're really going to be concerned with this visible light spectrum. Right. How many of you have ever seen light? Great. Great. Love the participation in this class. Here's a light source. There are really three things that light can do when it hits a different media, right? So light's going to travel through air, vacuum, whatever. Light will sometimes then hit another material, okay? That material can be glass, it can be water, it can be brick, it doesn't really matter, okay? There are three things that might happen. The first is called transmission. That means the light is going to pass through that material. And in this example, we're talking about air, and we're talking about glass. So if you think about the windows, how many of you realize light can come through a window? I know, it's like revelatory, right? So light can come through this window. Now, when the light comes through the window, it's actually going to bend a little bit, okay? So there's going to be some refraction there. We'll talk about refraction in a moment, so don't really wrap your heads around it too much. The second thing that can happen is called absorption. So light comes in, okay? It hits the surface, it becomes absorbed, and that turns into thermal energy. How many of you have ever felt glass that has been out in the sun? And it's always really cold, right, Monica? No, it's usually hot, right? Okay. Things that that absorb light, they become hot, right? The third thing is called reflection. Some of the light that's going to hit this surface is going to bounce off. Some of that's going to be related to the angle that the light is hitting the surface, and some of it's going to be related to the properties of the material itself. Okay? There are a couple kinds of reflection. One is specular. This is when you're hitting a smooth surface, so think about a mirror. Anybody ever used a mirror before? Nobody's ever used one, I can tell. No. Just as a heads up. I always think about, what about before mirrors were invented? Were people trying to like look in like water and try to figure out what they looked like? I don't know, right? It's like, why is my face rippling like that? Nobody thinks about that, right? Like, I don't know. I think about it. The other kind of reflection is diffuse. This is when the surface is not smooth. So do think about that rippling surface of water, right? You kind of see a reflected image in there, right? And it's sort of, it's not a smooth surface, okay? And when that happens, your light rays bounce off in different directions, and you do not have that nice, clean recreation of the image, right? When you look in a mirror, assuming it's not a magnified mirror, you get an undistorted reflection of the light that's hitting that mirror, right? Because it's a smooth surface. And when you look at the light that's hitting the surface of a pond, for example, it's not that high fidelity recreation of that image because the surface of the water is uneven, right? It's going to have some little waves and ripples. Questions about that? Not so bad, right? Hey, this is something. All right, we need to talk a little bit about a lens. Now we're going to talk specifically about the lens that's in your eye later. But right now we want to talk about lenses in general, okay, and properties of lenses. The purpose of a lens in general is to take this diffuse light source and take the light that's coming from it and refocus that onto an imaging surface. Not in this classroom, but many classrooms have projectors. That projector has a lens. Light comes into that lens, and that lens focuses the light onto the projector screen. That's the imaging surface, right? This is analogous to your eye. You have the lens right behind your pupil. Okay. Light comes in, that lens focuses it onto your retina, which is on the back of your eye. And we'll talk a lot about those details next week. So don't worry too much about it, just hang in there. So we're going to take this light source, collect the light through the lens, and then focus that onto an imaging surface. Occasionally, when that projector turns on, it's out of focus. The focal length needs adjusted, or the placement of the lens in the relative to the imaging surface, right? So every lens has a specific focal length. And what we mean by that is when light enters that lens, there's a specific distance from the lens to the imaging surface, and that will give you a clear, sharp image, right? Moving the surface, the imaging surface forward or backward is going to give you a fuzzy image. Okay? You don't have to share this information. It's personally identifiable medical information. Is anyone here or know someone who is myopic or hyperopic, nearsighted or farsighted? Okay, yeah. So several of you do, right? And I can take a guess that some of you who didn't raise your hands are also in that category, based on things attached to your face, right? Like glasses. The issue with either being nearsighted or farsighted is your eyes are not the right size for your lens, right? The lens of your actual eye bends the light too much or not enough, and it's out of focus when it hits your retina, okay? So someone who is nearsighted or farsighted would have light that comes in. Normally that's what we would have, right? But maybe all of those things intersect here, and your imaging surface needs to be there to get a clear image. By the time it comes back to your retina, Zoe, it's out of focus. That's a possibility. The other thing that could happen is it's too shallow, and now everything is in focus behind your retina. Right? Now the way that you fix this, Marissa, is you put another lens in front of your lens, and then you sort of pre-bend, either more or less, what is then going to come into your lens, so you get that nice focused image right on your retina. Okay? Does that make sense to everybody? How many of you just had an epiphany about why you wear glasses? Or contact lenses, it's the same thing. No one's going to admit to that. That's fine. Later we're going to talk about this thing called chromatic aberration. How many of you love telescopes? How many of you own a telescope? Is that a refractor or a reflector? Or is it a Schmidt-Cass?
It's it was built in like 1958 actually.
That's pretty cool.
Yeah, it's pretty nice. I'm still kind of rebuilding some of it. I'm going to finish my way on it.
It's exciting. I tell my wife when I retire I'm going to build my own telescopes. And I'd even like to grind the glass. I mean, that's going to take a while. So I can actually, I think she should be happy that I'm going to do, right? Because I won't be irritating her once I retire. I think her idea is I should probably not retire. Just like keep working indefinitely. Because I'm still not going to bother her and I'll make more money that way. So I think it works out to her advantage more so in that case, right? So we'll talk about that. Caleb actually will talk about why you might want a reflector versus a refractor, because there are different kinds of aberration that you have to worry about with different kinds of telescopes. So it'll be kind of interesting, but we'll get to that later. The other thing that a lens will typically do is it will invert an image, right? It'll kind of flip and invert an image. So if you look, here's an F, and if you notice, it's flipped and inverted that F by the time it gets to your surface. So this should really freak you out because Daniela, the whole world is upside down. Actually, there was an experiment they did a few years ago, a number of years ago, where they gave people glasses that inverted the world before the light hit their eye, and so then what they were seeing was everything upside down. Which is kind of crazy. You can imagine that would be disorienting, right? If you were looking at the world and everything was upside down. What's really cool about that is after they wore those glasses for a while, like one day they woke up and they were like, wow, the world's right side up, but I'm still wearing the glasses. Like their visual cortex was flexible and plastic enough to flip that. So then you were, even though it was still inverted, like inverted on your retina, your brain sort of flipped it back the right way. Once they took the glasses off, they had the alternate experience. For a brief period of time, they experienced the world upside down, but then it corrected itself. So that's pretty cool, right? How many of you would love to wear inverting glasses? Nobody's up for that? What if I said extra credit? Not that it's affiliated with the glasses, but I'm just going to see if that word in itself is exciting. All right. Other questions about lenses, focal length, invert flip, business? Everybody have a handle on that? It's not too bad. Whoa, look at this. this is super cool. This is a demonstration of transmission and refraction. This is light. Here's the wavelength, 650 nanometers at a 25-degree angle, and it's going from air to air. And so air has a refractive index of 1.0. This is a measure of how much that substance, that media, bends light. Okay? Air, we're going to say, does not bend light. So anything that comes into air, it's going to, when it comes out, it's going to be the same, right? Air is not going to affect the angle of this light. Now, there are many other things here that are kind of interesting. How many of you, this is kind of a fun one, water. How many of you have ever done the broken pencil trick? Where you walk over to one of the people that you hate and you break their pencil. No, that's not it. What you can do is you can take a glass of water and stick a pencil in it. And if you look at it from the side, the pencil looks like, instead of being continuous, it looks like it's two separate pieces, right? It's a great trick for little kids. You go, watch me break this pencil by sticking it in water. And they'll go, wow, and then you pull it back out and they're like, it's not broken anymore. And you're like, well, I imagine. I imagine this is a great trick if you do babysitting, to keep kids entertained for, I don't know, 6 or 7 hours. I think this would work. Probably about 30 seconds, right? They're going to be like, whatever. How many of you have ever been spearfishing? Nobody signs up for spearfishing? That's a thing, by the way. Right, so here's how this works. You like throw a spear at a fish. Also, people will like fish with bows, right? Anybody ever done that? Where you go fishing with a bow, and you're like, now here's the trick. You should tie a string to the end of your arrow, just to give you a heads up if you're going to try this, because you want to be able to like reel that in, right? So you don't just like shoot arrows into the lake. That's not a good idea. You want to be able to retrieve that. Now, if you had been spearfishing, you would know that don't stab your spear where you think the fish is, because of the refraction of the water. The fish is actually over to the side a little bit, right? And every time you miss the fish, it's going to laugh at you. So you have to plan for the refraction of water. So that's kind of cool. Now watch, we can increase the angle. Look at that. So, how many of you have a cornea? Or two? Thank you, Monica. We're signing people up to donate corneas. So I don't need any right now, but if you'll let me have yours, I'll freeze them for later if I do need them. Everybody's reluctant now to raise their hands. I left my scalpel in my office anyway, don't worry about it. I keep my scalpel in another building, actually. Heads up. True story, Justin, I have a scalpel in another building. You know that. Yeah. So, cornea has got a 1.38. That's like part of your eye, right? Anything that comes into your eye has got to come through your cornea, so it's already going to be bending the light a little, so that's awesome. It's like a free pre-bend there for your lens. On top of that, you've got a lens that has a 1.42 refractive index, so it's going to bend it some more just by itself. Now, we'll talk about how your lens can adjust, right? So hang in there for that. And then, who loves diamonds? No, but nobody's going to say they love diamonds. I appreciate that. All right, did you guys see that movie Blood Diamond? Anybody see that? Nobody's going to own up to that. It was actually a pretty good movie. And it'll make you think twice about precious gems. Because they like kill people for them. It's like really horrible process to like extract diamonds, right? So it's interesting to avoid that. So, refractive index of 2.42, that's actually pretty high. And again, we can change this angle a little bit. Okay. So, we see what happens here with this wavelength of light. This is 650 nanometers. We're going to perceive this typically as red, so not a big deal. Now, hey Caleb, do you remember that time I said, who here likes telescopes? And some guy named Caleb said, yeah, I do actually. And I said, hey, we'll talk about chromatic aberration in the future. Well, we're going to touch on it a little bit here. Whoa, that's actually pretty crazy. How many of you have ever had a prism? Anybody had a prism? Seen a prism? Okay, they're awesome. You shine light into it, and what happens? It separates the wavelengths of light, and it creates a rainbow, right? How many of you have ever seen a rainbow? Anybody ever chased that and caught the leprechaun and pot of gold at the end? No, it's impossible. Don't do it. It has to do with the light hitting droplets of water and then refracting that light and separating these wavelengths, right? So if you think about this for a minute, what you'll see is, let's change this. Sorry, the flash on this runs slowly. Hang in there. It's thinking. All right. I promise. It's doing something. Just wait. So exciting, right? What I'm going to show you is different wavelengths of light. Because they're different wavelengths, so we have different distance between the peaks, when it hits a new surface, it's going to bend at a different angle than other wavelengths of light. And this is why if you take white light and shine it into a prism, each individual wavelength of light will be bent at a different angle, and that's why they will separate. Give it just a moment. These flash demonstrations are actually pretty good, but they do sort of hog up processing power on the computers that may not be equipped to handle this, like really highly powerful flash demo, right? All right, give it just a moment. Let's see if we get this to go down. So we see 645. Hold on. Computer's frozen too. It won't let me. Oh, there we go. There's. We'll just okay. Let's try again. Okay. It's awesome, right, Justin? Let's see if we can get that to change to the lens in your eye. That's going to be more important to you than a diamond. No, nobody's making glasses out of diamonds, right? Think about that for a little while. This will work in a moment, I promise. And I only have 17 other flash demos to show you today. So, Imani, it's going to be... There you go. Look, it changed colors, right? So it changed colors because different wavelengths of light are perceived as different colors. Okay, so it's going to change a color as we change the wavelength of light. Notice that the way that it is bent and the effect of going from one media to another, or one medium to another, is actually different for those different wavelengths of light, right? And so it's going to vary, and that's why we separate things. This is why if you use a lens and shine a light into it, so a lens or a prism, the image that you get on the imaging surface is actually going to be separated just a little bit. Each color is going to be shifted. Okay? I think I clicked the decrease button quite a few times. Still see it's changing. Just hang in there. But it's a good demo, right? On a computer that has been produced in the last decade, this may work. So feel free to try this on your own computers. Not in the middle of something important, obviously, just in case it chokes up your memory. All right. So that was pretty cool, right? It's a little boring, but it was pretty cool. Now, this is actually important because this can be related to your lab activity that we're going to do here in a few moments. The intensity, so previously when we talked about intensity of a wavelength, we talked about amplitude, right? So we talked about loudness. In this case, we're going to talk about luminance. That's actually pretty cool. Natural surfaces can vary a lot in terms of luminance, right? What's interesting is how your visual system can respond to that. Who remembers that idea of gain control? And we talked about in relation to the sort of dynamic range of decibels that you could hear. Right now you're going to shift that sensitivity up and down. Okay? We do something pretty similar when it comes to luminance values. Now we're going to measure these luminance values. This is in candles per meter square. I'm not going to really hit you too hard on that. It's just a way that we can measure the intensity of light. Okay? We could also measure that in the number of photons. That's going to make you think about Max Planck, right, and those quanta and those photons. And we can measure photons per receptor, okay, because you have a number of receptors on the back of your eye. So these are different ways that we're really talking about the same thing, okay? How many of you have ever seen a piece of paper? It looks like this, typically, right? Give or take all your wonderful faces. And also the faces of the people I don't like, which there are a few on there. The starlight, anybody ever been outside at night? Okay. So in starlight, luminance is going to be pretty low, right? It's like dark. Okay. So you might only be getting 0.01 photons of light hitting each receptor. Okay. That's pretty low. If you take that same piece of paper into moonlight, you get 1 photon per receptor. Computer monitors, right? We're moving up, so now we're talking about like 63 candles per meter squared, right? So we're moving up. Room lights, if we think about the lights in this room, that's pretty getting brighter. The sky, think about how much brighter we are here, and then look at the paper in sunlight. Now if you look at this, you've looked at that same piece of paper in moonlight and you had 1 photon per receptor. You take that piece of paper outside into the bright sunlight, just like we have today. Look how bright and sunny it is outside. It's not very bright and sunny, is it? You will be getting 100,000 photons per receptor. How does your head not explode, Abby, when that happens? Right? I mean, if you think about this, right? Like what if I said, you're going to have to eat a cucumber. I don't know, I'm just thinking about a cucumber. You have to eat a cucumber. That's going to represent 1 photon per receptor as a cucumber. Right? And you look at that paper out in the moonlight. And then you take that paper out into sunlight and suddenly we're just shooting 100,000 cucumbers at you. Right? How many of you can eat 100,000 cucumbers? I don't even know if you can eat 100,000 cucumbers in your lifetime. I mean, that would be pretty impressive, right? I mean, you think about like, there's only 365 days. I mean, how many cucumbers can you eat in a day? 6? I think you'd vomit if you ate the 7th one, right? Does anybody think about these things? Nobody does. I don't know why nobody thinks about this. The point is, and it's a valid point, that's a massive increase from 1 photon to 100,000 photons. Also, my point, Monica, was it doesn't matter if you know what a photon is. Going from 1 to 100,000 of anything is a major increase, right? Okay. And we need to adjust our system, our visual system needs to adjust to be able to handle that. Otherwise, it would sort of explode and die, right? Because if you are only designed to handle one cucumber, and all of a sudden somebody hits you with 100,000 cucumbers, if you're not ready to adjust to that, you're dead. I promise you. I'm trying to do the math now, Montana, like how many cucumbers I could fit into this room. Because I'm thinking, like, how many cucumbers can you fit in a cubic foot, right? Because, like, I'd say, like, a cucumber is, like, not quite a foot, right? So I think, well, then, like, how many can I stack? And, like, I mean, can I put 100,000 cucumbers in this room? I think it's possible. You think it's possible? I think it's possible. That's a lot of cucumbers, right? It's a lot of photons. It's a big jump. You have to be able to get your visual system ready for that big jump. Otherwise, we would only be, so what if, here's the situation. Danielle, you can have one cucumber or 100,000 cucumbers. What are you going to do with 100,000 cucumbers? Nothing. How many of you shop for groceries? Okay. How many of you steal for groceries? Because I didn't see everybody's hands go up. How many of you just have a random grocery fairy who delivers things to your house and you don't have to pay for them? Can I sign up for that service? No, nobody has that. So, when you go to the grocery store and you buy, maybe more than one cucumber, you buy like 2 cucumbers for the week, right? I mean, that's like a reasonable number of cucumbers if you're an average cucumber eater, right? How many cucumbers do you think your grocery store has? Several hundred, right? I mean, they even have several thousand cucumbers. I don't know. But they have a lot of cucumbers. You aren't equipped to handle all of those, so you only take one. So it doesn't matter how many cucumbers they have. They could have 100,000. You're only going to take the one. That is fine for cucumbers, but it's not fine for your visual system, right? Because, Abby, if we go outside and we're only prepared to get 1 photon per receptor, guess what? We're missing a lot of information, okay? Those photons carry information about your world. And if we can only absorb 1 of those photons per receptor at a time, that's not going to help us. We're not going to be getting all the information that we need. So we need to be able to adjust our visual system so that we can handle more photons. Gain control is what this is called. Why did I use cucumbers as an example, Zoe? I think most of you know more about cucumbers than photons. And if I just said photons the whole time, you would have been lost. But cucumbers, you know. And that makes sense, right? All right. So what is light? And we want to talk about something called contrast and reflectance. Again, this is going to be the lab activity later. We'll give you the details on that. So that's going to be exciting. Right. Contrast is, and you're going to have to do this, so pay attention. Contrast is the measure of the difference between the highest luminance value and the lowest luminance value in a particular scene. This does not give you absolute information. This gives you relative information. Okay? How many of you were the greatest basketball player in your 3rd grade class? Madison was. Madison says she was the greatest basketball. Anybody in her 3rd grade class? Nobody. Hey, occasionally that happens. Nobody was in it. So we're going to take your word on this. You were the greatest basketball player in the 3rd grade.
Absolutely.
Absolutely.
Who told me?
Huh?
That's what my family told me.
That's what your family told you.
Yeah.
So that makes it even more true. Because your family would never lie to you.
Absolutely.
About how good you are at basketball, right? How, like in the absolute scale of things, amongst all basketball players, how great do you think you were in the 3rd grade?
Amongst all basketball players in the world?
Yeah, you were pretty near the bottom, right?
Yeah.
I mean, no offense.
No, it's true.
I'm sure, relatively
I
speaking.
didn't play after 3rd grade.
You just retired at the top of your game. That's great. You went out on top in the 3rd grade. So, we're talking here with contrast, we're talking about relative. We're just talking about comparing the dark and the light in a particular scene. We're not talking about absolute values, right? We're not saying, wow, that's the brightest thing I've ever seen. That's just the brightest thing I'm looking at right now. Okay? We're not saying you were the greatest basketball player ever. You were just the greatest basketball player in your 3rd grade class. How many of you know Flight of Condors? Is that the name of those guys? Nobody knows them? They have some phenomenal songs. They're actually a comedy group, and one of their songs is like, "You're the most beautiful girl in the room right now." Think about that a moment, right? It's actually hilarious. Because how many times, because this is Valentine's Day, so I got to ruin Valentine's Day for you. How many of you have ever been told you're like the most beautiful person in the world? And how many of you like believed that? You shouldn't, because I mean that's just like, I mean no offense to any of you, right? I mean, but this is a small sample size. There are like 25 people in this room. What are the odds that I have the most beautiful person in the world in this room? It's pretty limited, right? I mean, like the odds that happens, this is super small. So if any of you have been told that, that's probably a falsehood. And especially today. Regan, did you get told that today? Yeah, right? And you were like, whoa, wait a minute, no. That's not true at all. I mean, no, again, no personal offense to anybody. You might have just been the most beautiful person in the room right then. And that happens sometimes. So there you go, right? We've all been the most beautiful person in the room at some point. Assuming we've all been in a room alone at some point. There you go, right? So it's happened to everybody. Everybody has had that experience. But I think that song perfectly encapsulates contrast, right? It's about a relative measurement. It's not an absolute measurement, right? Does that make sense? So there you go. I don't know. Who's going to write that on their next Valentine's Day card? Justin, have you filled one out yet? No, you've got time to put it. You got time. You got time to make some edits there, right? Yeah. You're the most beautiful girl in the room right now. I think it's like the whole wide room right now or something. They make it almost sound like it's going to be something and then it's not. But it actually, I think, also on some other level, it actually is. It actually gives you some insight to actual relationships, right? And like, I don't know. So I'm just going to ruin everything for everybody, right? So I'm like this like sort of cynical person. Everybody's like, oh, soulmates, right? Well, you just happen to be close and acceptable. I think Taylor is much more likely, right? I mean, if soulmates, like whatever you define that as, exist, odds are you were close and tolerant. So there you go, right? So that's something to look forward to. I know some of you are thinking, like, how did you ever get married? Like, I'm certain some of you are thinking that, right, Marissa? Like, I'm certain, right? But I'm going to tell you, I've always been this way. So, as long as you're up front about things, that's fine, right? You can clip your toenails into the bathroom sink as long as you know that's how it's going to be, right? That's acceptable behavior if you know that, like, going in. Right? Now, if like 5 years in, and then you pick up a habit, then you can get slapped for that. But if you had it coming in, you're good to go. You're all in the clear. So there you go. Never try to be nice when you start a relationship. Try to be as horrible as you can. Because it'll save you time, right? Absolutely, right? I mean, don't try to be like extra nice to people because it's just going to set you up for failure later. Right? Be at least yourself, if not a little worse than yourself. And that way you'll know, like, is this person going to be able to tolerate me when I am sick, or when I'm grouchy, or when I've had a bad day because I had to go teach a sensation and perception class, right? Otherwise, it causes problems. So there you go. Never try to be your best self in a relationship. Try to be slightly worse than your actual self. That's all good relationships, I promise you, long-lasting relationships are based on that. And then anything you do above that, in money, that just makes life easier, right? So if you go in just being a little on the turd side of things, you're going to be fine. Contrast. Absolutely. I think my wife had the opposite approach. She was like, I'm going to be nice. There's a whole story about me yelling at a Girl Scout that I could tell you sometime. I didn't mean to. It was an accident. My wife still brings it up. It was like 13 years ago. Remember that time you yelled at that Girl Scout? She cried. I was like, no, she didn't cry. She actually came out ahead because I had to go buy more cookies from her because my wife was like, you really make that girl feel bad. I said, well, I didn't mean to. I just didn't want to buy cookies. All right. Contrast. It's relative. It's not absolute. That's what's important, right? So we're not looking at, that's the brightest thing I've ever seen, but that's like the brightest thing I can see right now. That's the darkest thing I can see right now. That's contrast. All right. Now, when we talk about reflectance, we talk about how much of the light that actually hits an object bounces off of it. Okay? That's what we mean by reflectance. What is something that's really reflective? Metal. Shiny metal, right? How many of you have seen shiny metal things? Look how they sparkle, right? I want that. And then you see something that's like dull and not so shiny, right? So here's a great example. We're going to talk about exactly the same thing. We're just going to talk about carbon. We've already talked about diamonds. What's the cool thing about diamonds? They sparkle, right? Everybody's like, woohoo, sparkles. Because they reflect a lot of light. They have a high reflectance, right? What's something else made out of carbon that doesn't sparkle? Coal, right? How many goes like, whoa, look at that sparkly coal? You've never heard that, right? It's the same thing, right? And you can save a lot of money by just giving someone a lump of coal and say, you know what? I'll bury this in the yard for you, and in like 10 million years, you'll have a super nice diamond. Oh, but see, I'm giving you all of these wonderful Valentine's Day gift ideas, and coal is one of them. It's useful. It's a practical gift. You can burn it, keep yourself warm. You can't burn a diamond. That's useless. All right, so reflectance. How much light is it going to reflect? The more light it reflects, the higher its reflectance. That makes some sense, right? Now, in natural scenes, so that's just sort of when you're out walking about, in here, this is considered a natural scene. You're not controlling things. We look at the contrast, for example, between a piece of coal and a sheet of paper. It's actually going to be constant, right? Because we're not changing the reflective properties of a piece of paper or a piece of coal just because I took it outside, or just because I shined a light on it, or not, right? The contrast is going to stay the same because the reflectance, the relative reflectance values stay the same. Now the absolute luminance values will shift up and down, right? Coal and paper are going to appear brighter outside in the sun than they are in a poorly lit room, but the contrast is still the same. Okay? Because the properties of that object, of those two objects, did not change, right? They stayed the same. Check this out. This is pretty awesome. What's super cool about this is the bar, like this bar in the middle, it's actually the same shade of gray all the way across, right? For most of you, it should appear lighter on the left than it does on the right, okay? And this is because of the surrounding gray. Make like another Valentine's Day reference and say like shades of gray, right? It's going anywhere. I'd like to make some comments on that. It's like, I've never seen those movies or read them. It's like because I'm an adult and I don't have to. I just, right? I mean, it's just, it's like, I don't know. I don't know. Contrast is important, okay? See, Madison, this is you in the third grade, where you looked like a super awesome basketball player compared to your third grade class. In reality, this was you in the third grade compared to Michael Jordan, who was much better at playing basketball. Okay? See, unfortunately, we're not so good. Even when you were in the third grade, Michael Jordan was still a lot better than you, right? Probably when Michael Jordan was in the third grade.
Yeah.
He was better than you when you were in the third grade.
Yep.
That's probably fair. Now, there is a mathematical formula that we will use, you will use, I won't use it, because I know how to do it. For your lab, you're going to do this. the mathematical formula to calculate contrast, and contrast will always be a proportion, somewhere between 0 and 1, right? I'm going to tell you why. It's the maximum luminance minus the minimum luminance divided by the maximum luminance plus the minimum luminance. And this creates that relative contrast, that relative measurement of contrast, okay? So what I'm waiting on now, Justin, is the producers of 50 Shades of whatever to like subscribe to my YouTube channel and like start hunting me down because I totally panned their movie which I didn't see. The last movie I saw was The Post at the theater, which was Tom Hanks and Meryl Streep. Good film. Wasn't the best Tom Hanks or Meryl Streep film. I mean, they both turned in better performances, but they always turn in great performances. Even it was a good movie. Bob Odenkirk is in it. For those of you who are Bob Odenkirk fans, in a very serious role. You guys know Bob Odenkirk. Better Call Saul. Isn't that Bob Odenkirk? Anybody know? Nobody's going to admit to that. There you go. Abby, I expected you to know. I thought you were a Bob Odenkirk fan.
I mean, I am a fan of the guy that you're talking about, but I don't know his name.
That's Bob Odenkirk.
Okay, we'll agree.
We'll agree. Thanks. I appreciate that. All right. Contrast, maximum value of luminance, minimum value of luminance. We're going to compare those. We're going to get a number. If it's 0, that means that the maximum and the minimum are exactly equal, right? Okay? Because when you subtract one number from itself, you get 0, and when you divide that, you get 0. If it's 1, and in reality you're probably never going to get 1, that means that your minimum luminance is actually 0. It's absolutely 0. Okay? And your maximum is going to be some number not 0. Okay? And when you subtract and add, then you can, don't worry about it. But it's going to be between 0 and 1. So you can get things that are really high contrast or really things that are really low contrast. It's pretty awesome. Hey, this is cool. Let's see how many slides do I have left. So I'm going to give you time to do the lab activity. Okay, we're fine. This is sort of interesting. This is about wavelengths of light. How many of you, there aren't a whole lot of incandescent lamps anymore. Actually, these may be. I can't really look up into those can lights. Let me turn them off. Are those incandescent bulbs, can you tell? Or are they fluorescent? They look like they're incandescent bulbs. So we have fluorescent lights in the drop ceiling there. You quite often have fluorescent lights at home. Anybody use CFLs? That's the squirrely pigtail looking lights. Okay. So those are fluorescent bulbs. The old bulbs that you would buy, like the older style that were cheaper, right? That also when they explode, they don't kill you with mercury. So that's why you shouldn't just like break. The CFLs have a little mercury in them, right? That's why you have to dispose of them properly. I know you don't, but I'm just telling you that you should. They actually have a different sort of signature of wavelengths, right? Very much like when we talked about harmonics. We talked about different wavelengths combining to make one sort of output. It's the same idea here. Incandescent lamps, if you look at the wavelength and then their spectral energy, right? They have they're most powerful up there, right at that 700 nanometer, right? Which is actually going to appear to be that sort of red shifted, right, or yellow. How many of you are really into photography? Anybody? How many of you have been in community theater? How many of you have ever seen a theater or spelled theater? They use different lights with different colors and different filters, right? And so they can get different effects on stage, right? And so that's sort of important. Daylight, I'm assuming most of you have experienced daylight. It actually sort of has the peak around 450 nanometers, which is typically perceived as blue. Have you ever noticed what color the sky is? It's blue, right? The sun is mostly throwing out blue light. Okay. here's your lens and your retina. Think about this in terms of, we want to talk about lens, we want to talk about focal length. It's about 16.8 millimeters. Some of your eyes are bigger or smaller than that. That's fine. Assuming that your lens has also properly adjusted to that size, then you're cool. If not, if there's that mismatch, remember, you can either focus in front of or behind your retina, and that will give you fuzzy vision, either hyperopia or myopia, right? So you're either going to be near or farsighted. No worries. We're not going to worry about calculating visual angle, that's fine. Oh, this is actually kind of cool. This is accommodation. If your eye is relaxed, so everybody relax your eyes. Not your eyelids, but your eye itself. So don't do this. That's relaxing your eyelids. Do this. Did you notice the difference? I'm gonna do it again. Ready? You guys ever seriously, you ever like try to focus in on things? Nobody does that. I do that. So, parallel rays that are coming from distant objects fall into focus on the retina, right? Okay. So when they're coming in, they're going to come into your eye, and we're going to focus those on your retina. Not a big deal. Rays that are like from near objects or things that are farther away, they'll actually be focused somewhere else, so you're not going to see them, right? So if you look out into, like I look out into this class, and I want to, for whatever reason, focus on one student or another with my eyes, how I do that is I can change the shape of my lens so that the light reflecting from students farther or closer away comes into focus instead of the light from elsewhere, right? So I can take that lens, you just kind of bend it into a different shape, right? And then it's going to change the way that the light rays are bent. And so then light from like here, for example, could be focused, or light from way out here could then be focused on the retina. Okay? So it's called accommodation, which is pretty cool. Guess what happens when you get old? This doesn't work so well. And that's why some of your parents need longer arms when they take you out to dinner. Because they hold the menu way out here, right? Anybody do that? See their mom, their dad? Here to hold this for me so I just want to see if I want the fettuccine Alfredo. It's because they're not able to adjust the lens. At that point, you need to take them to the eye doctor. Or, if you're lucky like me and you have siblings, tell them to take them to the eye doctor. So I don't actually have to do it. Thankfully, my mother is already prepared for actually, she's already decided my sister is going to be in charge of making any decisions about whatever happens to her, because I think she knows not to trust me. Myopia, no worries, we talked about that. Hyperopia, we talked about that. If you have glasses or photorefractive keratectomy, that sounds exciting, right? It's when they take a laser and they shave your cornea. Sounds like a lot of fun. That's a close shave with a laser right there. They can change remember your cornea had some ability to bend light. Remember it had some refractive power. We can change that a little bit. All right. Oh, hey. This is actually kind of cool. I just want to keep checking to make sure because I need to wrap this up soon. Oh, okay. We're good. Some of this we'll skip through. This is sort of an old study, so there are some things in here that people would probably do differently now, and there are sort of some interesting things we could talk about. We're going to skip some of those, but we'll talk about this. Pupil change. Your pupil, right? You guys know you have pupils, and they change in response to the amount of light. They also change in response to whether or not you see something that you like. Okay. So this is kind of interesting. So they had this study, this was back in 1960. They had pictures. They had a baby, a mother with a baby, they had a nude male, a nude female, and then they had a landscape. And they would show people these pictures, and they would measure the change in their pupil diameter, right? And this is by percentage. So the gray bars here are for females and the blue bars are for males. So if you were to show a female a baby, she would probably get, 15 to 17 on average % increase in pupil diameter, right? So, okay, so I saw baby. No change for males, you see that over here. That's interesting. A mother and a baby, though, you get a slight increase with the pupil size in males. There's some really interesting ideas behind why this might actually be going on, probably beyond the scope of this class. Nude males, right? You see an increase in both males and females. Pupil diameter, a bit bigger increase for females. Sort of the opposite is for nude females. And then landscape, I don't know, I always thought this landscape one was kind of cool. A little bit of an increase for males, but an actual decrease in pupil diameter for females. I don't know. I always thought that was kind of cool. These are less sort of surprising from some evolutionary standpoint, right? I mean, they're sort of not as, but I don't know, the landscape one I always thought was kind of a cool thing. I like to also think about this, so I'm going to tell you two stories. One are about people with beady eyes, don't trust them. So I think about like people with beady eyes, right? You ever seen somebody with like beady eyes? Probably don't like you. And they don't like you because their pupils are getting small. They got to squint to be able to see you. Who is that person I don't like over there? So they have beady eyes. Because your pupils get small when you see something you don't like. Right? And then how many of you have heard of eye makeup? So here's the idea behind eye makeup. You want to make your eyes look as big as possible so that when someone sees you, they will think you like them because your eyes are bigger, right? And so it's a trick. And so if you make your eyes look and not beady around, make people think that. Women used to do this, used to put like drops of like paralytic plant extract in their eyes, and that would dilate their pupils, so their pupils were bigger. And so then when somebody saw them, they would go like, "Whoa, she must like me. Look how big her pupils are." No, it's not really. That's not really a comment you hear people say, right? So there you go. Nobody's finding this as interesting as I did. The second thing about giant pupils, though, is like a real problem. The bigger your pupils, the worse your vision, actually. So if you have really big pupils, the light can actually hit all the edges of the pupil, and it gets all kind of diffracted and spread out. We'll talk about that more later. So you have a really fuzzy image. So I don't know if this is like the best way to go about your life with like giant pupils. So there you go. Anybody have any comments on that? Concerns? Anybody going to walk around squinting now so people think you hate them? Anybody going to walk around like this now? So this is what you should do. Like if you're having trouble making friends, so I don't know if this ever happened to you. You have trouble making friends, walk around like this and people will definitely start hanging out with you. Hey guys, you want to go out to eat? It's actually really painful in my head. I like the beady eye better. Leave me alone. This is my face during office hours. Don't come in here. Your eye has photoreceptors. You got like 100 million of these. They respond to light. You've got cones, sensitive to highlight levels. Most of them are in this area called the fovea, right? Which is kind of, it's a little off center, but it's at what we call the optical center. That's kind of like AJ, like true north and magnetic north. They're slightly off. Right? If you were to actually find the center of your eye, wouldn't really be where the fovea is, but that's the optical center. Okay, not a big deal. You also have rods. They respond to low light levels. They're actually outside of your fovea, so they're like on the periphery, right? Here are some things that are, this looks like a rod, and that looks like a cone, okay? Not a big deal. Here's kind of, I think this is like actually a really cool representation of your retina with like rods and cones out here. So like your rods are out in the periphery and your cones are in the center. So I think that's actually a fairly decent representation. They're going to contact a variety of other cells we'll learn more about these later. You've got things called horizontal cells, you've got bipolar cells, amacrine cells, and then you have ganglion cells. Again, don't worry too much about this right now. We're going to really hit this next week. The smaller your photoreceptors, the better, right? Because the smaller they are, the more detailed your analysis of the visual scene, right? How many of you love video games? How many of you play video games? Right, so what's like the latest cool video game people are playing these days? Super Mario Brothers 2? No. What's a cool video game?
I play Fortnite.
Fortnite, right? And how are the graphics on that?
Pretty good.
Yeah, have you ever played any of the original like Atari games? And they're just like cubes, right? So it's like, what is that? Okay, so that's like if your photoreceptors are big, you get the cubes, right? You get these really pixelated view. If you have small photoreceptors, then you're gonna have a really detailed image for Fortnite, right? So if you think about, like TVs are that way, right? And so the smaller the pixel, the more pixels you have, the better the picture, right? And that's exactly the same idea with your photoreceptors, not a big deal. You have a thing called the optic disc, we'll talk about that later. That's a spot in your retina where you don't have any photoreceptors. All right, what do we mean by resolution? That's the ability of the eye to see fine spatial detail, right? If we say you can resolve or you have high resolution, right? So if you think about what's a high resolution television, right? You have really small details and you can see things, right? And you can like count the hairs on someone's face. That's a high resolution TV, right? Low resolution TV, you don't even know someone has a face. It's like, well, I hear someone talking, but I don't know, right? Something's moving. When we talk about sensitivity, we're talking about how low can the light level be and our retina still get excited. Okay, we're talking about how good are we at detecting just a few photons. That's sensitivity. So sensitivity and resolution are two different things. Okay. Then we have this cool thing called the Nyquist limit. We're going to talk more about the Nyquist limit later, especially once we revisit spatial vision. But essentially, we're thinking about light as a wave here. It goes up and it goes back down, right? And if you want to detect this peak and this trough, you need two receptors. You need one to detect the peak and you need one to detect the trough, right? If you only have one receptor and there's a peak and a trough, then it's going to go like, sort of middle, right? So, but you need to be able to detect the peak and the trough. We'll hit this concept again, but I want to introduce Nyquist limit to you now. This is going to be a recurring theme. Spatial vision is complicated and difficult, but we'll be fine. We're going to talk a lot about square waves and sine waves and these gratings, okay? So if we look at these dark bars and light bars, these are clear, crisp edges, right? And if we kind of look down and we see like where is their high luminance, that's going to be the wires, and the black areas are going to be the low luminance. The transition between here is very sharp. It creates a square if we plot that, right? That's what we call them, square waves. Sine waves, if you notice, it's sort of fuzzy, that transition. So if we were to plot where is it dark and where is it light and how is it in between, it's some intermediate value, and we get that sine wave gradient. Not a big deal. Spacing is important for the photoreceptors, right? The closer they are, the better for resolution. Sensitivity is limited by what we call photon noise. Okay? There's some random rate of photons hitting your eye, right? And that random rate is going to be more than 0. Okay? And if it's more than 0, then that's raising your sensitivity. So you're going to to know that you have a signal, it's going to have to be above that baseline level, right? Remember before when we talked about signal to noise ratios? Okay, we're kind of revisiting the same concept here. All right, Caleb, are you ready to give your part of the lecture on telescopes? No, you're not. That's fine. I am prepared. Just in case you weren't, I came to class prepared for this. This is just showing you what's called chromatic aberration. I think this is a little better drawing than the one I tried to create, Marissa. But if you see here, this is for like blue, green, and red. Really, we're thinking short, medium, and long wavelength, and we'll talk about why that's important later. But if you notice the focal points for each of these 3 wavelengths of light are actually in different places. So if your retina was here, the information from the short wavelengths of light would be right in focus, but the other 2 wavelengths would be shifted. Now our brains have to make adjustments for that, right? And they do. If you have a telescope, on the other hand, Caleb, and you put a lens in there, and if it's a refractor, right, you have to worry about this chromatic aberration and this shift in wavelengths, and then you'll get some sort of, and this happens at all telescopes, you'll get some kind of fuzzy image, right, because the wavelengths of light will separate a little bit as they come through this lens. You have to adjust for that. Spherical aberration is similar. If a lens, not the one in your eye, because the one in your eye is actually, we'll talk about how cool that is. It's actually set up so it actually has a varying refractive power, so it's not the same refractive power all the way through. But if you look at this, you get a sharper angle coming out here at the ends of the lens, because most lenses are tapered, right? That's how you get that change in the focus. But that's going to create different focal points as well. Your lens in your eye is structured differently, so that actually out here you have a different refractive index than you do in the middle, and that times the wavelengths of light together, so they all come out and they can focus on one spot. We'll talk more about that next time. Hey, who loves optimal eyes? Bigger eyes will always give you better resolution, because bigger eyes will give you a what we call a smaller interreceptor angle. And this is sort of something to think about. So if you think about the visual world that's measured in degrees, right? When light comes in to your eye, we have to take this whole world and we have to shrink it down to your retina, right? And when we do that, we only have a limited number of receptors. If your eye is bigger, then you have more receptors per degree of visual angle, right? You can get a better resolved image. The problem with bigger eyes is you have to have a bigger head. If you have a bigger head, your mother has to have bigger hips. To save you a little time on this, if she has bigger hips, she's not going to be that great at walking. Okay? So as a species, we've sort of hit the optimal head size to hip ratio for females, so that we can still like run from things. So that's important. So our eyes are about as big as they're ever going to get, unless our hips get bigger. So there you go. In case you don't know, for those of you that were born, hopefully that's most of you, you sort of had to, typically the way that you get out is through the hips, right? Okay? And that doesn't always happen. Sometimes you got to go out the escape hatch, and they'll cut that hole for you there, and they'll pull you out that way. But that's not the way it happens in the wild. So the humans out in the wild, when that was the thing, they did not have the option of, you know, C-sections and so forth, right? So you just had to squeeze them out. Something to look forward to. Or not, which is what I would prefer you do. Right, Regan? All right, pupil size, we already talked about that, not a big deal. Oh, eye movements. So we should talk briefly about eye movements. You make all kinds of eye movements. You've got 6 muscles that can move your eyes about. There are things called saccades. These are these rapid eye movements, right? They'll last just a few milliseconds, and you can kind of just move your eyes around, not a big deal. Voluntary pursuit's kind of cool. How many of you have been watching the Olympics? Anybody been watching that? That's been a thing, right, on TV? How many of you have been watching and you like kind of like, oh, there's like somebody moving, so I can like track them with my eyes, right? That's cool. The really weird thing is this is a cool experiment actually. So imagine that thing you were watching recently where you were like tracking like a dog running. I don't know if you were watching the Westminster Dog Show instead. Try to move your eyes in smooth pursuit of something that doesn't exist. And you can't do it, right? So if you try to imagine, can't do it, can't even do it. You try to imagine, like I think about this, like I'm going to watch a butterfly, I'm going to start over. No, you'll always make a saccade. There's no way around it. So you can try it, and you think like, but you jump. You're going to make these like quick jumps to try to approximate something that's not there. You can only do voluntary pursuit if there's actually something that you're focusing on and pursuing. It's actually kind of cool. We have this thing called vergence. That's when you bring your eyes close together to focus on something, right? You can do this trick, like watch your finger do this. That's vergence. Your eyes are going to come in and out. We talked about vestibulo-ocular movements. You can pick a spot, continue to stare at it. And did we talk about nystagmus? Any optokinetic nystagmus? This can happen. Sometimes you'll have like a bunch of saccades and then kind of a smooth pursuit, and a bunch of saccades, and then a smooth pursuit. You can induce this with like rapidly changing dark and light kind of flashing things. But sometimes happens to folks with head injuries. Also happens to folks who are drunk and you lie them on their side. Right? If you lie down while you're drunk, then your eyes will do that as well. So, I know, right? So like the next time you're around someone who's drunk, you're going to just like push them over and watch. Why do they move? Helps with spatial resolution. Not a big deal. Keeps most of the important stuff at the fovea, where we have most of our photoreceptors. That's important. Also important, we'll talk about depth perception later, but it's important to kind of get that binocular information, right? All right. Any questions? Awesome. That was